Thanks, Filippo. And again, thanks for the invitation. So let us give this broad presentation about the issue of heterogeneous treatment effects in two-way fixed effect regressions and some solutions that have been proposed recently to address this issue. So the starting point is the following. So let me say before that I will do the first 30 minutes and then Clément will finish this general presentation, and I will stop talking about the issue related to the traditional methods, and then Clément will talk about some alternative solutions that have been proposed. So the starting point is the fact that, as Filippo said, a lot of research implies the so-called two-way fixed effect regressions. And so this is what is referred to as TWFE in the slides. So remember this acronym. So this, let me spend just a little bit of time on this regression because they will be very important afterwards. So here we mean regressions where we are interested by the effect of a treatment that is called D here on some outcome variable called Y. And we have some data, some panel data, typically, at a group level. So group is indexed by G, and for periods T, let's say. And these regressions include fixed effect both at the group level and at the time level. Okay, so the alpha G and the gamma T in the equation. The rationale for doing this. Oh yes, okay. Can I increase the volume too, or maybe it's fine like this? Huh? I don't know. Is it here? Maybe channel. Okay. So I'll try to speak louder. So the rationale for doing this is the following. So let me give you the example of the effect of minimum wages in the US on employment. This is a topic that has attracted a lot of attention among economists. And what people have used very often is this type of regression conducted at the county level where T would be a year typically. And so the idea is to say, well, the counties in the US are very diverse. Probably a county in California is very different from a county in Montana, say, and this will explain a large part of the differences in employment. So we are not really interested by these differences, but we are interested by the effect of minimum wage, which can change, let's say, for instance, in California at one period of time, but not in Montana. And basically, we want to account for the effect of the differences between California and Montana, and we will do this through the alpha G, right? And then there could be also effects of time. And in this example, this is just because you can have a recession at one moment that will, of course, affect employment or a boom, an activity boom. So you're not interested by these effects either. And on the other hand, you may be interested by the fact that that particular year, California has decided to increase minimum wage, and that could have also an effect on employment. Okay. And so because there are always macroeconomic shocks like this, there are very often differences between units like those between California and Montana. It's very common to have this type of regressions. Okay. And so just to give you a sense of how common they are, we just conducted a recent review literature, so just on the American Economic Review, actually. And we try to identify the 100 most cited papers in this journal between 2015 and 2019. And it turns out that more than a quarter of these use at least in one part of the paper such regression. So it gives you the idea of how pervasive they are. Okay. And it's not only in economics, this is also true in sociology, environmental sciences, etc. Okay, so another view of why two-way fixed effect regressions are popular is that they were considered to be some form of generalized difference in differences. So difference in differences are situations where you want to compare just two groups, let's say. To take the initial example of Card and Kruger, this would be New Jersey and Pennsylvania. And between two periods of time, in Card and Kruger, I think it was in 1992, between the end the beginning of the year and the end of the year, but I may be mistaken on the exact periods. And basically look at the difference in evolution between New Jersey, which introduced an increase in the minimum wage, and the evolution in employment of Pennsylvania, which did not. Okay. And the thing is that this estimator is appealing because if you believe that absent any change in the policy, New Jersey and Pennsylvania would have evolved in the same way. They could be different initially, but they would have evolved in the same way. Then this difference in difference estimator identifies the average treatment effect of the policy. So here in this case, this increase in the minimum wage in New Jersey. So this assumption that I told you, the fact that they evolved in the same way absent the policy, is a so-called parallel trend assumption. And be careful, try to remember these signs, these two lines, two parallel lines. This means parallel trend assumption, right? Okay. So the thing is that people believe that once they run two-way fixed effect regressions, they were actually doing a kind of generalized version of this difference in differences. And this is true if you have two groups and two periods of time. The two are completely equivalent in this case. But what people have realized recently is that actually once you have more than two groups, more than two periods of time, and maybe you have a more complicated design, maybe groups, so in this minimum wage example, maybe there will be one change in California in 1995, and maybe there will be one change in Montana in 1997, etc. Then in this case, it's no longer true that you will identify average, so causal effects only under this parallel trend assumption. What you also need is that the treatment effects are constant between group and over time. And the issue is that this second assumption is often implausible. If you still think about this example, it's plausible that in periods of recession, the effect of minimum wage will not be the same as during a boom. Okay, and it's also plausible that the effect of the minimum wage is not the same in a pretty poor county where a lot of people are paid at the minimum wage as in a much richer county where most of the people are not paid at the minimum wage. Okay. So the fact that for these the two-way fixed effect regression to make sense, we needed this second assumption. This has conducted a lot of research on this topic, and in particular in two dimensions that we will discuss. The first is to try to diagnose the importance of this issue, and the second is to propose some alternative estimators. And that's what I'm going to talk about right now, and Clément as well. So these are the papers that we will discuss, some briefly and some more in details. And yes, as you can see here, we are going to talk about unbiasedness, but we don't pretend to be unbiased ourselves. As you can see, there are a lot of work by me and Clément, just for the reason that we also understand, at least we hope, these papers better. Okay, so let me start by discussing the issue with these regressions, what exactly do we mean by robustness with respect to heterogeneous treatment effects, and whether we believe it's an important issue or not. Okay, so a first result in this direction is to show that so the coefficient of this two-way fixed effect regression will correspond on average to a causal parameter, but not exactly what we would like to. Precisely, it would be the weighted sum of the TE in equation 2, and the TE are the treatment effects for group G at period T. So in my example, this would be, for instance, if I just consider low minimum wage and high minimum wage, this would be the effect of moving to a high minimum wage for a group G, which could be, okay, a specific county in California at period T. Okay. So basically, this regression identified a weighted average of treatment effect. And if we just say this, we could think, okay, this is fine. This is pretty intuitive. This regression gathers all this data together and aggregate all the treatment effects that we are interested in. Another good news is that actually all these weights, the W, are known, as they can be computed very easily. And we actually developed commands, so stata and R commands called TWFE weights that you can use in order to compute them. Now, to be a bit more negative, a first issue is that these weights are not proportional to let's say, the true weights, the weights that you would like, which would be the size of cell GT compared to the overall population. What you would like to do in reality would be, okay, I would like to take all the treatment effects of everyone, of every county in the US, let's say, and then weight these differently, because maybe this county in California is much more populated than this county in Montana, and then we want to put a higher weight on it. The first issue is that these WGT do not reflect that exactly. Okay. Something that is probably much more worrying is that these weights may even be negative. So maybe the term weight is not completely appropriate, because actually you can have negative weights. Okay. So why am I saying that it's worrying? Well, it means in this case that it could be that all the treatment effects are positive, and yet because of the negative weights, the coefficient that you get with the regression is negative on average. So this means that the estimator could be very misleading. Everybody benefits from the policy. So maybe, I don't know, in this example, maybe every county would benefit from a high minimum level of minimum wage, but actually you get a negative coefficient, or vice versa, of course. Just to give you an example of this, imagine that you have only two groups that are treated. So here in this decomposition, we only care about the groups. You see that the sum is only for the groups that are treated, that receive a positive treatment. So imagine that you have only two groups which are treated, and one has a weight of 2, the other has a weight of -1, so the two weights sum to 1. And then the first group, so the first cell, so G1, T1, has a corresponding treatment effect equal to 0.5. And the second cell, G2, T2, has a treatment effect of 2. So everybody benefits from the treatment. But yet, if you just use our formula, you find that on expectation, the estimator will be equal to -1. Okay. So you have just a very simple example here where everybody benefits from it, yet you find a negative effect. So let me try to give some intuition of this result. In order to do so, I'm going to focus on a specific design, which is a situation corresponding to what we call staggered adoption. Staggered adoption is when the treatment increases only once. So just a simple example that Clément will discuss is the effect of unilateral divorce laws on the rate of divorce. So this is something that has been studied several times in the research. And in this example, all the states initially didn't have the possibility to have divorce unilaterally, but then some states change over time in the US, but not at the same time. And some states did not adopt this policy. Okay, so this is an example of a staggered adoption design. So with this particular example, what you can show is that the regression coefficient beta hat FE is actually a weighted average of two types of difference in differences. The first type of difference in differences is not problematic. This corresponds to standard difference in differences, where you compare groups that switch to treatment from groups that remain untreated. Okay, so in my unilateral divorce example, you compare states that adopt the law at the period that you investigate with other states that do not. Okay, so that corresponds to the DID 1. And then you have other types of DID that I refer to in the slides as DID 2, where you compare groups that switch from no treatment to treatment with groups that are both treated at both dates. And these D2 are the problematic difference in differences. These correspond to forbidden comparisons, let's say. Okay. And because you are taking a weighted average of these two types of difference in differences, this second type of difference in differences will lead to these negative weights. You can actually compute the weights in this weighted average derived by Goodman-Bacon using the Stata and R packages Bacon decomp. So I'm not going to give you some formulas, but I can try to illustrate what I just say with this graph. So in this graph, it's probably the most simple example we can think of. We have 3 periods of time. We have 2 groups, and one group becomes treated early, and the other one becomes treated late. So it could be like two US states, and one decides early on to switch to a high minimum wage, while the second switches after the first one. Okay. So the two dotted lines correspond to what would happen to, let's say, the level of employment without the treatment. And the parallel trend condition states that the two lines for the early group and for the late group are in parallel. Now at period 2, the early group becomes treated, and then because the early group becomes treated, it diverges from the dotted line, because now we don't observe Y0 for this group, but we observe an outcome which reflects also the treatment effect. And in this example, the treatment effect is positive. The late group remains at a level corresponding to the dotted line because it is not treated yet. And then at the third period, the late group becomes treated. It is positively affected by the treatment, and then it's beyond its level. It's above the level it would have without the treatment. Okay. But now what we do with the two-way fixed effect regression is actually first difference in difference, where we compare early and late between period 1 and period 2. And here we see that the difference in difference will be positive because the black dot at the second period is above the dotted line. But then we will do also the D2. And you can see that D2 will be negative because the increase for the late group is not as important as the increase for the early. Okay. Because of that, the D2 will be negative. And in this example, actually, the beta hat will be also negative, despite the fact that the treatment effect is positive for everyone. So this is one issue, one reason why we have some trouble with the two-way fixed effect regression. And a lot of people in this literature has focused on this specific type of problem, but actually there is another reason why this regression can be problematic, which is that when the treatment is not binary, which happens often. So in the minimum wage example, maybe you don't want to just indicate low or high minimum wage, but the true value of the minimum wage. Then in such situations, actually, you are also running implicitly in this regression some comparisons between groups that switch more to more treatment, let's say, to groups that switch to less treatment. So in my minimum wage example, you may end up comparing groups, counties or states that increase a lot the minimum wage to other states that also increase the minimum wage, but by a lesser amount. And if you have just two groups, two periods of time, actually you can do the math very easily. And in this case, the regression coefficient would be a ratio between the standard diff and diff on the outcome variable and the diff and diff on the treatment variable. And here the M corresponds to the group that increases more and L corresponds to the group that increases less. And this ratio, what we can show is that this ratio in general will not identify a weighted average of treatment effects or a convex combination, more precisely a convex combination of treatment effects, which means that we will have the same issue. It may be the case that everybody benefits from the treatment, but still the coefficient is negative.
Xavier, allow me to interrupt for a question from the floor. I think this last thing that you presented partly answered it, but the question, and I hope I'm paraphrasing correctly what it says, asks about modeling this heterogeneity in effect. In particular, the question asks whether using threshold effects in the two-way fixed effect context can help alleviate the bias, with the example of the minimum wage, whether if, for instance, the level of the minimum wage increases beyond a given level, this relationship between minimum wage and employment may change, or whether we can model cross-country differences in the effect.
Okay, yes, thanks for the question. So the answer is yes, but you have to be very sure about the way you specify heterogeneous treatment effects. In the sense that you will avoid these issues if you are able to fully capture heterogeneity in treatment effects. If not, you will still get a bias, and actually in some cases you can even prove that the situation could be worse. So this is something on which I cannot give more details because it's a bit more complicated, but you get some additional contamination biases. So you have to be very sure about your modeling of the heterogeneity of treatment effects. So here this illustrates again graphically what is happening. So in this example, you have just two. So you see in this example, you have no variation in timing. The two groups get treated at the same period. And so the issue arises just because one group gets more treatment than the other, and potentially groups do not have the same level of treatment effects. So in this example here, the group that receives more treatment is in black, the one that receives less treatment is in gray. And here again, we have the parallel trend that we can see through the dotted lines that evolve parallelly. And if you basically the regression coefficient in this example corresponds to some up to some proportional term to the diff and diff in the y's. And here in this example, the group that receives less treatment is much more positively affected by the treatment than the group that receives more treatment. And because of that, its outcome increases much more to a point that actually it becomes larger than the outcome of the first group. And because of this, the difference in difference in this example will be actually negative. Though again, in this example, the treatment effects are positive. The treatment effect, for instance, for the group M is the difference between the point at period 2 and the dotted line at period 2. So both treatment effects are positive, yet the estimator is again negative. Okay, just to give you a more concrete example, so with Clément, we revisited a paper by Gensko, Shapiro, and Sinkinson asking what are the effects of newspapers on electoral turnout, and they answered the question using some US data between the end of the 19th century and the beginning of the 20th century, and what they do is a first difference regression of the evolution of turnout on the evolution of the number of newspapers between two elections. And they found a positive coefficient, which is highly significant. In this example, they did not do exactly the same regression as the two-way fixed effect regression, but we have a similar result in our paper with Clément. And then we can compute the weights. And it turns out that a lot of the weights in this example are negative. So almost half of them. And they are not only negative, but some of them are high enough so that they sum to more than -1 on absolute value. And this means that this issue of heterogeneity can be quite important. Okay, so I don't have much time. So maybe quickly, let me try to present the issue with event study regression. So for now, I just presented a static version of the regression, but oftentimes we are interested by a dynamic version where we also care about the past value of the treatment. Okay, because maybe what matters for the example of unilateral divorce law, for instance, it's very plausible that the effect the first year the policy is introduced is not the same as the effect 10 years afterwards. And we want to capture that, right? And actually, we also want to see whether the assumption of parallel trend is plausible, and we do that by including some coefficients corresponding to the fact of being treated in the future.
Sorry, Xavier, for interrupting you. Before you jump into this new case, there's a question from the floor. If the treatment effects are increasing with the treatment dose, is this second bias still possible? I think it was referring to the previous example.
So in this case, we would not necessarily get a sign reversal, but still we would get a bias. Okay. All right. So basically, in this dynamic specification, we get a result which is very similar. And this is shown by Sun and Abraham. So you have in equation 4, the same kind of, the first term is very similar to what we had with Clément. But then there is an additional term, which is new and which corresponds to so-called a contamination bias, if you want, because now you have not only the issue of heterogeneous treatment effect in the first term, but you also have the fact that treatment effects for other periods of time. So for instance, I'm looking at the effect 2 periods after the introduction of the policy. Actually, the instantaneous effect is also contaminating this coefficient. Okay. And this introduces a new reason why this estimator can be biased. Again, the W, the weights can be computed in this example, and Sun and Abraham have developed a stata package to compute these weights. So I think I'm done, more or less on time, I hope. So I leave the floor to Clément.
Okay. Hi, everyone. Thanks for inviting us today. So I'm going to take over and talk about the heterogeneity robust definitive estimators, meaning the alternatives that have been proposed in the literature to try to propose estimators that rely on parallel trends assumptions, like the two-way fixed effects regressions. And we like parallel trends because it's an assumption that's partly testable by looking at pre-trends, but that do not rely on the assumption that the treatment effects are homogeneous, which is the feature that we do not like about two-way fixed effects, because in most cases, this homogeneous effects assumption is going to be implausible. Okay, so that's what we call heterogeneity robust diff-in-diff estimators, estimators that rely on parallel trends like two-way fixed effects, but that do not rely on the homogeneous effect assumption. And we're going to see that, you know, there is a whole literature of heterogeneity robust diff-in-diff estimators that may look a little bit terrifying at first, but the underlying idea is extremely simple. The part that Xavier did earlier is extremely important because it allows us to understand why two-way fixed effects is not robust to heterogeneous effects. And like Xavier said, two-way fixed effects is not robust because it makes two types of forbidden comparisons. The first one is you compare two switchers, a switcher more to a switcher less. That's not robust to heterogeneous effects because if the effects for the two switchers are different, you could have sign reversal. So that's the first type of forbidden comparison we're going to try to avoid. And the second type of forbidden comparison is to compare a switcher, someone going from untreated to treated, to someone treated at the two dates. Okay, and there, that's not robust to treatment effects that would be changing over time. Okay, so that's the second type of forbidden comparison we're going to try to avoid. So essentially, the name of the game in this literature is going to be to try to be a bit more careful than two-way fixed effects and avoid making those forbidden comparisons. Then the type of estimators that have been proposed are going to depend on whether or not we want to allow for dynamic effects. What does it mean to allow for dynamic effects? Or rather, what does it mean to rule out dynamic effects? That means that we are ready to assume that someone's outcome at time t only depends on their treatment at time t, not on their previous treatments. Okay. Allowing for dynamic effects means we allow for the possibility that my situation today depends on my treatment today, but also on my treatment of yesterday, the day before yesterday, etc., etc. So the estimators that the heterogeneity robust estimators we're going to propose are going to depend on whether we allow for dynamic effects or whether we rule them out. So obviously, it's more appealing to allow for dynamic effects, right? Because it relies on fewer assumptions. But we're going to see that there is actually a pretty steep cost in allowing for dynamic effects in the sense that heterogeneity robust diff-in-diff estimators that allow for dynamic effects are going to become very complicated, hard to interpret, and very noisy, potentially, when the design is going to get complicated, when your treatment is, for instance, not binary or non-staggered, or this type of situations. Okay, so first, we're going to assume that there are no dynamic effects. In that case, we propose to focus on, is there, no, there is no, yeah. So in that case, we propose to focus on this delta S parameter, which is the average treatment effect on the switchers being the GT cells whose treatment is not the same, those GT that are such that the treatment of group G is not the same at period t and at period t-1. Okay, so in the Card and Kruger example, a switcher would be, I never remember, New Jersey, I think, would be the switcher, and Pennsylvania would be not a switcher. Okay, and so to estimate that parameter, the idea will be to form two types of diffs in diffs. Whenever we have a switcher that goes from untreated to treated, it goes from a treatment of 0 to a treatment of 1. We're going to compare its t-1 to t outcome evolution to the outcome evolution of a stayer who stays at 0, okay, between t-1 and t. So we avoid making the forbidden comparisons of comparing a switcher to an always treated. On the other hand, when we have a switcher out, someone going from a treatment of 1 to a treatment of 0, that may happen, then we want to compare that unit to a stayer whose treatment stays at 1, at t-1 and at t. And the first type of comparison, the DID plus for the switchers in, is going to rely on a parallel trend assumption on the untreated outcome y0, while the second one is going to be valid on a parallel trend under a parallel trend assumption on the treated outcome y1. So this DIDM estimator only relies on parallel trend assumption, one on y0, the other one on y1, but it does not rely on assumptions that the treatment effect is homogeneous. And it's computed by our DID multiple GT theta and R commands. Importantly, the thing we like about parallel trends is that it's a testable assumption. We propose placebo test of the assumption. What's the idea? Well, the idea is that the actual estimator compares the outcome evolution of switchers and stayers when the switchers switch. The placebo is going to compare the outcome evolution of switchers and stayers just before the switchers switch to verify if before the switchers switch, we indeed observe that the trends of the two groups were parallel. So this, like I said, this DIDM estimator relies on the assumption that you have no dynamic effects, which is not always plausible. A great benefit of imposing that assumption is that it's very easy to extend this DIDM estimator in many directions. For instance, extending it to discrete rather than a binary treatment is straightforward. It's pretty easy to extend it to have covariates, etc., etc. We implement this estimator in the Genskow et al. Application that Xavier already mentioned. And you remember, or maybe you do not remember, that the two-way fixed effect estimator was 0.0026. I think I've written and seen that number sufficiently many times that now I know it by heart. And you see that the DIDM is pretty different. It's almost twice larger than the two-way fixed effect estimator. So using an heterogeneity in this application, using an heterogeneity robust estimator does make a pretty large difference. And in fact, Xavier did not show you that perhaps the reason why Genskow and co-authors use this slightly unusual first difference specification rather than the more standard two-way fixed effect specification is that the two-way fixed effect specification is actually giving you a negative coefficient, okay, which is a bit counterintuitive. The fact that newspapers would reduce political participation was perhaps not what the authors expected. So that might be why they run the first difference specification and giving them a more expected positive coefficient. But this is to emphasize that here in this example, if we compare DIDM with two-way fixed effect, which is the thing that people typically use, we actually get a sign reversal. Okay, so that's an example where the heterogeneity robust estimator do make a very large difference with respect to standard practice. And perhaps our conjecture, it's hard to have a proof of that, but our conjecture is the fact that, as Xavier showed you earlier, that's an example where when you compute the weights attached to the two-way fixed effect regression, you see that you have many and very large negative weights. And that might be the reason why when we use an heterogeneity robust estimator, then we find something that's pretty different. But I want to emphasize that that's an example where the heterogeneity robust estimator makes a big difference. It's not always the case. And now we're going to see another example where actually the heterogeneity robust estimator mostly confirm what you would get with two-way fixed effects. Okay, so now let's allow for dynamic effects. When we allow for dynamic effects, we need to modify a little bit our potential outcome notation. When we rule out dynamic effects, things are simple. Your outcome at time t only depends on whether you're treated or untreated at time t. So you have two potential outcomes, y0, y1. When we allow for dynamic effects, things get much more complicated because your outcome at time t depends on your treatment at time t, your treatment at t-1, etc., etc. So even if your treatment is only binary, the simplest case, at day t, you actually have 2 to the t potential outcomes. Okay, you have your y of 0, 0, 0, 0, meaning you've been treated from period 1 to t. Your y of 0, 0, 0, 1, meaning you've been treated from period 0 to period 1 to t minus 1 and treated at t, etc., etc. So just the modeling becomes much more critical. But so that's what we are going to do now, because we want to allow for dynamic effects. So we're going to review 2 families of estimators. The first family of estimators have been proposed by Sun and Abram and Callaway and Santana. We're going to review those of Callaway and Santana, but keep in mind that Sun and Abram have also proposed very similar estimators. So what's the idea of Callaway and Santana? So they focus on the case where the treatment is binary and staggered. And that's really the cost of allowing for dynamic effects, which is that when you allow for dynamic effects, it's going to be feasible, I'm not going to say easy, but feasible to propose estimators that are robust to dynamic effects in the binary and staggered case. Whenever you get out of that case, things get much more complicated. But so in the binary and staggered case, Callaway and Santana start by noticing that you can aggregate groups into cohorts, okay, into cohorts, and that start receiving the treatment at the same period. So in the unilateral divorce law example, you're going to have that US states adopt unilateral divorce laws at heterogeneous times. And so you're going to have, for instance, the dates are not going to be accurate, but let's say the 1982 cohort, which are going to be Nevada, Nebraska, and Arkansas, that adopt the unilateral divorce law in that same year. So that's the 1982 cohort. So the building blocks of the analysis in Callaway and Santana are what we're going to call this TECC plus L parameter. That's the average treatment effect at date C plus L among the cohort that started receiving the treatment at cohort C. So at that time, cohort C has been treated for L plus 1 period, okay, from C to C plus L. So that's an effect of having been exposed to the treatment for L plus 1 periods. So to estimate this treatment effect, their idea is pretty simple. They say we can use a diff in diff that's going to compare the C minus 1 to C plus L outcome evolution in that cohort C that started getting treated at C and in never treated groups, okay, assuming that we have never treated groups, which is the case in this unilateral divorce law example. So the idea is say, okay, the baseline year is gonna be C minus 1, the year before the cohort starts getting treated. The last period before treatment is going to be our baseline. And then we're going to compare outcome evolution from that baseline to L year after they started getting treated between that cohort that got treated and the never treated. So then Callaway and Santana, potentially this TCC plus L estimator might be a little bit noisy. Like if in my example, if in the 1982 cohort, you only have 3 states. The treatment group has only 3 units. So maybe you're going to get something very noisy. So what they propose is also to aggregate those TECC plus L estimators across C, across cohorts, but not across L. Meaning that, for instance, you compute the instantaneous effect for L is equal to 0 of the 1982 cohort, the 1983 cohort, 1984 cohort, etc. And then you aggregate them, and that gives you an average instantaneous effect across cohorts. And then you can do the same thing for L is equal to 1, which will give you an average effect 1 year after treatment, etc., etc. And then you can plot them into a nice graph, and that gives you your standard event study graph. So another thing they do is they propose, so instead of using the never treated as controls, you could use in this diff-in-diff estimator that compares the C-1 to C+L outcome evolution of cohort C. You could use not only the never treated groups, but you could use any group that's not yet treated at C+L as a control group, okay? And there are a number of advantages of doing that. First, you get a bigger control group, so that probably is going to increase the statistical precision of your estimator. A second advantage is that maybe those groups that get treated at some point are more comparable to those early treated groups than the never treated. Okay, so maybe the parallel trend assumption is a bit more plausible when you also use as control the not yet treated. And in fact, in practice, applied researchers sometimes completely discard never treated groups from their analysis and only leverage variation in treatment timing for their identification, which reflects this intuition that perhaps we think parallel trends is more plausible when we only look at groups that eventually get treated. Okay, and so they have like two commands. So the CSDID in Stata and DID in R commands that compute those estimators. So then there is another family of estimators, which we're going to call the imputation estimators. So that have been proposed. Actually, we're not putting all the references here. So Borosiak, Jarvan, and Smith, but also a paper by Gardner and another paper by some political scientist whose name I don't remember, but who should also be credited for that proposal. What's the idea? So at first sight, the estimators look very different because you see, like Callaway Santana, we have something, it's really just diff-in-diff, some non-parametric diff-in-diff estimators. Here it's going to be a regression estimator, a more complicated two-way fixed effects regression. What they say is that instead of saying of regressing the outcome on group fixed effects, time fixed effects, and just one treatment indicator that's equal to 1 for every treated GT cell, they say, okay, we just need to estimate a much more flexible two-way fixed effects regression. We need to regress the outcome on group fixed effects, time fixed effects, and one dummy for each treated GT cell. Okay, so potentially you can have a lot of treatment dummies in that regression. And they say, well, the estimator of the treatment effect in cell GT is just going to be the coefficient on the dummy for that cell. And what they show is that under parallel trends and also the assumptions of the Gauss-Markov theorem, then their estimator is blue, is the best linear unbiased estimator of the treatment effect in in treated cell GT. And because the estimators of Callaway and Santana are also linear estimators, that means that the estimators proposed by Borosiak, Jarvan, and Spies must be more precise. Okay. What's very important to keep in mind is that this is true only under the assumptions of the Gauss-Markov theorem. And the one assumption that's particularly strong is that there should not be any serial correlation in the outcome of a group over time. Okay, so to come back to the minimum wage example, the employment of New Jersey at time t should be independent of the employment of New Jersey at time t+1, which is clearly not very realistic. And there is actually a very, very recent paper that shows that this efficiency comparison between the two estimators, the fact that the BJS estimator is more efficient than the Callaway and Santana estimator, actually that reverses if instead of assuming no correlation, you assume on the contrary, very strong serial correlation, okay? And those estimators, they are computed by the DID imputation Stata package. So now let's try to understand a little bit the difference between the two estimators. So the great thing about the Callaway-Santana estimator is that it has a very simple closed form expression. The BJS's estimator does not have a simple closed form expression in general, because it's a regression estimator, except in a special case where you have no variation in treatment time. Okay? So you think of your basic, actually Karl and Kruger type diff-in-diff, their estimator has a closed form expression. which allows us to compare the two. And so in that case, let's assume we have only one treated group S and that starts getting treated at date TS. To estimate the treatment effect in that group L period after adoption, the Callaway-Santana estimator is just going to compute a diff in diff, comparing the TS-1 to TS plus L outcome evolution of the treated group and of all the control groups. Okay, so we just look, the baseline is the year before adoption, and we look at the evolution from that baseline to TS plus L, and we compare the treatment and the control. The estimator of Borosiak-Javelin-Spiess is going to do something very similar, but a little bit different, which is that rather than taking the last period just before adoption as the baseline, it is going to average across all 3 periods, which under the parallel trend assumption is also valid. Okay, if you have parallel trends from TS-1 to TS plus L, well, if you have parallel trend for any pair of consecutive periods, then you will also have parallel trends from that average period between 1 and TS-1 and TS plus L. Okay, so that's a valid thing to do. And because they use, because this estimator is using more pre-period to construct the baseline, intuitively you may think, well, yeah, okay, it's always going to be more efficient than this one. It's using more information. Well, actually, that's a little bit misleading. That is true under if things are IID, but if, on the contrary, things are very strongly positively correlated, maybe actually using all this pre-period can actually become harmful. Okay, so it's not always good. Yes?
Yeah, I was going to interrupt you just precisely on that point, Clement. I have 2 questions from the floor. The first one is the issue of serial correlation and the extra assumption that we need to meet for the VJS estimator. The question is, do you refer to serial correlation conditional or are conditional to the fixed effects component?
If we conditional, I guess, yeah, because it's within group. Yeah. Good, very good question. So here we are.
Yeah, sorry.
Oh, yes.
Do I need to repeat that?
Yeah, so it's conditional. A very good question. It's conditional in the sense that it's within each group. Do we have that their potential outcomes tend to be correlated over time?
And the second question is, can the issue with serial correlation of the outcome in that estimator be addressed by using the first difference instead of the...
Yes, so, but it's kind of... yes, very good remark, because, and you, yes, so the... So yes, it can, but then if you do that, then what you're going to end up doing is kind of Callaway and Santana, actually. So you're right that, you know, this, should I do BGS or should I do Callaway and Santana? And which one is going to be more efficient is actually very related to that whole discussion in the panel data literature as to whether one should use fixed effects or first difference. You should use fixed effects if you have no serial correlation. You should use first difference if you have, on the contrary, very strong serial correlation. Actually, that the in the sense that the errors follow an AR1 process with a coefficient of 1, a random walk process. In that case, you should use first difference. So it's a bit the same here. If you have that things are independent, you should use BJS. If you have that things follow that the errors follow a random walk, you should use Callaway and Santana. The issue, I would say, at this stage of the literature is that both assumptions are unrealistic. Things are not IID. Things do not follow a random walk. And then when probably the reality is that you know, probably the errors follow some AR1 with a coefficient of 0.5. Which estimator is the most efficient in that case? It's not clear yet, actually. Okay, but those are efficiency considerations, okay? There is another and perhaps more first order concern, which is bias. So we've assumed parallel trends, okay? We assume that trends are parallel. Under parallel trends, both estimators are unbiased. So on that, then on that margin, on that measure, they do not differ. In practice, I think that many people, at least I, tend to think of parallel trends as not something that's perfectly true. Okay, we're not in an experiment. In an experiment, we would know that trends would be exactly parallel, but we do diff in diffs in non-experimental settings, where what we hope is that doing diffs in diffs, relying on parallel trends, is a bit better than just doing cross-sectional comparisons. It's going to lead to less bias estimators than if we were to do matching, for instance. But there is no reason why trends should be exactly parallel. In that world, in a world where parallel trends holds almost but not exactly, then the two estimators may have substantially different biases, actually. If you think, for instance, of a world where the treated and the control groups are on their own specific linear trends, then differential trends are going to be widening over time. Okay, so the longer the horizon over which you compare the groups, the larger the differential trends. In that world, probably the Callaway and Santana estimator is better because it's comparing the treatment and the control groups over a shorter horizon than the Borosiak and Jarvel estimator, which compares them because it looks at all the pre-periods to construct the baseline. It's comparing them over a longer horizon. Okay, and perhaps the bottom line is that, so, you know, like it's not necessarily such a big first order question which estimator you should use, because in practice they tend to give very similar results. And actually, if they don't give you very similar results, then that means that the parallel trend assumption must be violated. Okay, under parallel trends, those two estimators are unbiased for the same parameters. So if you find that what they give you is significantly different, that means that parallel trends must be violated. Okay, so I'm already a little bit out of time, so I will go very quickly over a second application. Revisiting a paper by Justin Wolfers on the effect of unilateral divorce law on divorce rates. So he uses a 1968 to 1988 state level panel data in the US. And you have that over that period, about 30 US states adopted a unilateral divorce law. What's very important for the results we're going to see now is that that's a very simple design. The treatment is binary, staggered, and on top of that, you have a very large group of never treated, okay? 21, so almost more than 40% of US states are never treated. And this type of designs, binary staggered plus many never treated, are actually the type of designs where two-way fixed effects are the most robust to heterogeneous effects. And that's a little bit what we're going to find here. Here, I'm showing you the effects of unilateral divorce laws on divorce rates. On the x-axis, you have the relative time to the change in the law. So 0 is the time of adoption. And then we go all the way up to 15 years after. To the left, we have placebos. We're comparing the states that adopt and do not adopt a law before the adopters adopt. And you see that according to all the methods, two-way fixed effects, Sulan-Abraham, Callaway, Santana, etc., you have no pre-trends. The placebos are small and insignificant. And you do have a large positive effects, short-run effect of these laws on divorce rates. And where the methods disagree a little bit more, it's about the very long-run effects, which according to some methods are significantly negative, but according to other methods are still negative, but not really significant, but the differences are not very large. And so the bottom line is that here, if you look, so you know the wide scale is the same for the 6 panels, and you see that the magnitudes are pretty similar. So here, that's an example where two-way fixed effects and the heterogeneity robust things do not give you very different results. Okay, yeah, so this literature has shown that two-way fixed effects may not estimate a convex combination of effects. The literature has provided alternative estimators mostly for the binary and staggered case. We think that developing more estimators for non-binary or non-staggered treatment is very important. And we also think that it's at this stage, it's still a little bit unclear whether researchers should always completely abandon two-way fixed effects regressions, because they sometimes do estimate a reasonable convex combination of effects, especially in simple designs. And they often have a lower variance than heterogeneity robust definitive estimators. Okay, thank you very much.
So thank you very much, Clément and Xavier, for this great presentation. I also would like to thank Javier Terrero and Douglas Sutherland and Nisse Silsen that helped organize this seminar. I think we are, I see that there are open questions. We are a little bit out of time with this. So what I propose, you will stay with us in the afternoon, touching some of these points more in detail. So maybe I suggest that we close the session now, and then we'll try to address this question in the rest of the afternoon to give an opportunity to people, the busy people, to go if they'd like. So just as a reminder, we'll start again in 15 minutes with an in-depth class on the topics that Clément just showed us. Thank you very much.